Okay, thanks for the presentation and good morning to everyone. I am Martina Totaro and I am a PhD student at the University of Messina. Today I'll talk about the advanced characterization of basalt fiber reinforced composite using energy methods. In the current scientific scenario, basalt has been proposed like a good alternative for the synthetic reinforcement for composite materials due to its low cost and reduced environmental impact. The present work in particular was conducted in the field of a bigger project that aims to compare the mechanical behavior of basalt and glass composites in order to assess the possibility of replacing glass fiber with basalt fiber composite for structural application. Anyway, in this presentation, I'll show just the results related to the basalt mechanical characterization performed using the thermographic method. So first of all, I want to introduce the thermographic method. During a cycle fatigue test of common engineered materials, the temperature evolution of the specimen surface detected by an infrared camera is characterized by three phases. An initial rapid increment, then a plateau region, and then a very high further temperature increment until the failure. The more we increase the applied load, the more the temperature of stabilization will increase and the number of cycles will decrease, and the energy parameter will be constant. Based on this consideration, the thermographic method consists of plotting the sigma squared and the delta temperature of stabilization, then in drawing a linear regression and the intersection between the x-axis and the linear regression will be our fatigue limit. So notice that the stabilization temperature is reached in a short number of cycles. So it is possible to apply in a stepped way the stress level sequence, recording the stabilization temperature for each step until the failure. In this way, it is possible to evaluate the number of cycles at which the specimen would break if it were stressed only at the stress level sigma I. And we will obtain some points that are represented by number of cycles and stress level. And in this way, we can build the Wheeler curve. Also, with the static test, we have the possibility to make prevision about the fatigue limit of the material with the static thermographic method. During static tests of common engineered material, the temperature evolution on the specimen surface is characterized also in this case by three phases. An initial linear decrease due to the thermoelastic effect. Then the temperature deviates from linearity. And then a very high further temperature increment until the failure. The transition between phase 1 and phase 2 will be the sigma limit, that is a good estimation of the fatigue limit. I want to precise that this method, the static thermographic method, is still object of research. So it is well established for metallic materials, but not for composite. So in this study, we are trying to apply the static thermographic method also on composite. About the specimen, the panels were made by vacuum infusion by Intermarine Messina. The resin is vinyl ester. From these panels, we extracted rectangular specimens that you can see in the photo. At the microscopic image, you can see the lamination sequence that is 090 type woven, and the number of plies is 6. For the experimentation, we use a servo-hydraulic load machine of 250 kilonewton. And in order to monitor the behavior, the thermal behavior on the specimen surface, we use the air camera of FLIR. We carried out 3 types of tests. The static tensile test performed in displacement control at 2 mm per minute. The stepwise fatigue test, and the classic fatigue test, so in constant amplitude, constant stress amplitude with a load ratio of 0.1. Here there is the stress strain curve. The curve is not increasing until the failure, but we can notice that there is a first load loss that is due to a fracture in the external part of the specimen. Then we have a clear load drop that corresponds to the delamination of the specimen, followed by other fracture on the external part. Our consideration regards all the sigma of delamination that we consider as the first damage of the specimen. And it is about 375 megapascal. Here there are the results related to the static thermographic method, so the energetic release of the material. According to the theory, we can see that in the initial part of the delta TT curve, a linear trend is visible. Then the temperature deviates from linearity, showing a variable slope between the two different cases. And it is possible to draw a true linear regression and to determine the coordinates of the meeting point of the two strain lines. But we have to notice these two steps that may raise some doubts, because the intersection between the phase 1 and the phase 2 could also be associated with it. So static test is really influenced by the common issues of the composite materials, like the presence of voids or intrinsic defect. So we need to have a confirmation with the static thermographic, with the thermographic method that is an official method. So it can help us in understanding better, interpreting better these results. So we move on the fatigue test, the stepwise fatigue test. We use the load ratio of 0.1. The initial stress is 50 megapascal and the final stress is 140 megapascal. The delta for each step is 10 megapascal, and each step lasts 20,000 of cycles. Here I put it together, I combined the results related to the fatigue, the stepwise fatigue test, and the thermographic method provides a fatigue limit of 96.5 megapascal. In support of stepwise fatigue test, we have done also constant amplitude fatigue test that provides a runout at 100 megapascal, that is near to the fatigue limit, performed with the thermographic method, a delamination of the specimen at 110 megapascal, and the breaking at 120 megapascal after 1 million of cycles. Then we put all together the data and we built the Wheeler curve. We also added some data from the literature, and we can say that our data fits well with the literature ones. So from the stepwise fatigue test and the constant amplitude fatigue test, we realized that the fatigue limit of the material aligns precisely with that phenomena that we were not able to interpret in the static thermographic method. And we also have done other static tests to confirm this interpretation. And we definitely can say that the first phase is linear and decreasing, and the second phase has a variable slope between the different cases. The sigma limit, that is the sigma of first damage that we found, is about 100 megapascal. So we can say that the static thermographic method is really complex for composite materials, and because we have a significant variability in the results, so it is required that a particular attention of the operator. I am at the conclusion of my presentation, and I want to summarize my results. So the energetic release during tensile test of basalt fiber reinforced composite has been evaluated. We found the limit stress with the static thermographic method of about 100 megapascal. The thermographic method provides a fatigue limit of 96.5 megapascal, and the constant amplitude fatigue test demonstrated the lamination of the material at sigma of 110 megapascal and the breaking of the specimen after 1 million of cycle at sigma 120 megapascal. We are going to make other experimentation in the basalt to confirm these results, but we have still started the characterization of the glass composite. I finished and I thank you for your kind attention.